She didn't give us our countdown, but it's time to start. Just here, you got it? All right, sorry about that. That's all recorded. That's going to be a great start to the class. So picking up where we left off, remember it was supposed to be generators, Wednesday, but we did problems and it pretty much took our entire time doing the problems. Hopefully that was beneficial for you, and especially because you had the homework because it got postponed till today. Do you remember the homework is due this evening, though? Yes, Leslie.
So the OpenStax, you were able to...
I was able to move it, yeah.
Okay, because I noticed that. I was like, just making sure.
Yeah. All right. So we've learned about the Hall effect. Remind me, your forgetful teacher, what is the Hall effect?
It allows us to detect changes in current. Basically, it's like a current difference or charge difference on a current. So a combination of those words will work.
It is a combination of those words. You're not wrong. What are you saying here?
Doesn't it have to do with voltage?
Okay, it has to do with voltage. It's when we have a current passing in an electric or a magnetic field, then there will be forces on the charge carriers in the current that will create a voltage across the charge carrier. And so we're going to start by looking at that aspect a little more here. Now, this is no longer technically the Hall effect because we don't have the right situation for a Hall effect. But if we have a metal conductor, remember what a conductor is. A conductor is something where the electrons, some of the electrons, can move with virtually no energy cost. So the electrons can move around to position themselves wherever is best. So if we have a metal conductor and we move it in a magnetic field, it's electrons that can move, so we're only going to focus on the forces on an electron. So if I have this moving and I have electrons, the electrons are going to experience a force. And remember, how do we find the direction of the force on a moving charge? We use the right-hand rule. Because these are electrons, remember you're going to have to reverse the answer. Because your force is Q V cross V, and Q is negative. So it's in the minus V cross V direction. If you want to really confuse yourself, you can use the left-hand rule for negative charge and the right-hand rule for positive charge. But there's no point in confusing yourself. But you do have to be aware. Negative charge reverses the direction. So if we take this rod that's moving to your right, index finger goes to the first item in the cross product. I'm going to actually write the equation down just so people don't have to look it up. I know not everyone memorizes the equations, especially because I tell you don't have to. So there's our equation for the force. So what should my index finger be pointing parallel to? Is that velocity. So my index finger is pointing parallel to velocity. Then I orient my hand so I can point my middle finger in which direction? The magnetic field. So that is, the X means into the screen, and so my thumb points up. And so what direction is the force on the electrons?
Down.
Down, because it's opposite of the upward result of V cross B.
Wait.
Because of the negative charge. The negative charge reverses it. Go ahead.
So does it have to state that it's negative, or anytime it's an electron?
Well, the electrons are always negative.
Yeah.
If it's it's your force is in the direction of Q times V cross B. So we use the right-hand rule to find V cross B. And then we have to multiply that by Q. So we have upward for V cross B, and then we multiply up by minus 1.602 times 10 minus 19. The minus means minus up or down.
So it's always going to be negative, or when is the case when it's positive?
Electrons are always negative.
When you're talking about protons, that's when it's going to be.
Protons have positive charge, right?
Yeah. Okay, just wanted to make sure.
Michael, do you have a question?
So the the right-hand rule, are you saying that because of electrons move in the opposite direction of the positive direction, you know, to negate
Because electrons moved.
in the opposite direction? That's
Well,
what you have to
the force on the electrons, because of the negative charge, is in the opposite direction of the V cross B. So our force on the electrons is down, which of course was shown here. And so the electrons are going to move down. So I'm going to now develop a negative charge here and a positive charge here. Why will I have a positive charge at the top? Negative charge at the bottom is pretty simple because there's a force pushing electrons down. Why is there going to be a positive charge at the top?
Because the electrons are leaving the top.
Because the electrons are leaving. Right. So since the electrons are gone, what's left is protons without those extra electrons, positive charge. Now we form an electric field because we have a charge separation. What direction is this electric field going to point? Electric field always points out of which charge? Out of positive and into? So in this case, we have an electric field inside of our conductor. Do you remember when I said there's no electric field inside a conductor? There was a caveat that I gave you with that so that I wouldn't be lying. If it's in stationary, equilibrium situation, here it's not stationary, it's moving. And because it's moving, if you also had a changing magnetic field, it would do this too. So it's not just the moving. You have to be, conditions are stable. Then you would have no electric field. But here you actually have a force on those charges that's going to force it to have an electric field. And this is going to be a uniform electric field. Why? Well, our symmetry. And so if it's a uniform electric field, then the electric field strength is the voltage difference across those two sides divided by the separation. In this case, that D is this distance here. So the outcome of this is that I'm going to create a voltage difference on the rod that is delta V is equal to the electric field. Actually, I shouldn't have put a vector sign there because I didn't put it. The actual equation is like this, but because it's uniform, I can just make it like that. So I have voltage difference that's the electric field times D. And how does the electric field relate to force?
If you apply the charge, like if you apply a charge, isn't it force?
And again, I didn't show the vector signs, but that's right. So now I'm going to take my final step. When I reach an equilibrium situation, which is going to have an electric field because of the motion, my equilibrium situation is going to say that my electrons now are no longer making one side more negative, the other side more positive. So the net force of the electrons is zero when I reach equilibrium. So when I reach equilibrium, I'm going to have some of the forces equal to zero. Now remember, there's directionality to this. I am just going with magnitudes. I'm going to set magnitude of force B is equal to the magnitude of force E. And so that's going to be QVB. Why is the force magnetic? Up here I put the force vectors QV cross B. Why did I right now just write force magnetic is QVB? There's an important aspect that has to be true for me to make that change.
From what to what?
From the red equation there, force is equal to QV cross B, to the green equation at the bottom that says force equal to QVB. Okay, the vectors have to be perpendicular. You said normal, right? The vectors have to be perpendicular to each other for me to make that change. Otherwise, I would have had times sine of the angle between them. So my magnetic force is QVB, and my electric force is QE, notice right away that the Q's are going to cancel. So I have VB is equal to E. So the electric field is the speed times the magnetic field it's going through. So we have this relationship between the electric field that's produced, the speed, and the magnetic field. And now finally, using this relationship, I can say that the voltage difference across that baby is going to be equal to the length of it, D, times the speed at which it's traveling, times the magnetic field. Good. Or is that just thinking? Okay. Now, let's think about where this may matter. If I run around the house going like this, am I going to develop a significant voltage difference from fingertip to fingertip? Why not?
You don't have magnetic force.
Well, there's the Earth's magnetic field is 0.05 Tesla. So it's a pretty small magnetic field. My speed is pretty small, and my distance, my wingspan is under 2 meters. So I'm not going to develop a very big voltage difference. So I can't go like this and run around and shock people. Rubbing my feet I can, because rubbing my feet I can develop a much higher voltage in the thousands of volts. But what goes around like this that moves at a fast speed and has a much longer reach? Airplanes. And they're made out of conductors conveniently enough. So the airplanes are going to generate pretty big voltages from one side of the wing to the other as they go through the Earth's magnetic field because they have high speeds and they have a much bigger distance across the airplane wings. So I'll probably give you a homework problem to ask you to find the voltage difference on an airplane flying. It might have some orientation, so you actually have to use that sine theta. So we call this emotional EMF, and I've not emotional EMF. I have already gone through everything up to here now. Here is another example of emotional EMF, but now we have a resistor. So if I move that slider, it's going to make a voltage that we calculate just like we just did. Now notice here, I have a very precise equation that has the directions all taken into account. V cross B was the equation we had in the force, and so it still maintained that V cross B instead of just putting V times B. And then we had the electric field times distance, or not times distance parallel or dotted with the distance is the voltage. So we have this dot this, and we have all of our directions taken into account. If you're doing something and you have to use this form, right, if they're not all the right orientations, do this calculation first, find the angle between V and B, use the right-hand rule to find the direction of that resultant, and then find the angle between this resultant and the length. And remember, with the dot product, it's the magnitudes times the cosine of the angle between them. Cross product of the magnitudes times the sine of the angle between them. But the outcome of this is, in this case, my velocity is perpendicular to my magnetic field, and my length is perpendicular to those. And so V cross B dot L is just V times B times L, because that's the case we just did. And so we develop a current. Now, this here is fundamentally what Faraday's law of induction says. It's not exactly the same, but it's fundamentally the same. We can go from Faraday's law of induction to get this equation. So I'm going to jump forward about 7 slides. I tried to rearrange the slides, but I'm going to jump forward a bunch of slides to, actually I should ask this question first. Where does the electric energy come from to produce the current that is then dissipated? The energy is dissipated in the resistor. Where does that energy come from? It's not a question we cover, but it's an important conceptual idea. The first law of thermodynamics, we can't create or destroy energy. It's got to come from somewhere, and it's indeed the work done to move the rod. So if I have this apparatus and I push the rod and let go, it's going to stop even if there's no friction, because it has kinetic energy when I let go, and that kinetic energy is going to be turned into the electrical energy dissipating resistor, and as it does, it has to slow down. Why? Because there's a force, right? We started with this talking about forces. There's a force being placed on that rod due to the magnetic field. And that force is moving the electrons. Okay, now jumping forward. A whole bunch of slides forward. There it is. Faraday's law of induction. So Michael Faraday, when I was a kid, I read a biography of Michael Faraday, and I got all excited. So every time I see his name, I still think, wow, this guy was such a genius. And people hardly talk about him. For a while, the Lost TV show was popular, and there was a guy, I think his name was Faraday or something, and people realized, hey, this is a famous guy. So what Faraday realized was that, well, we know if you move that conductor, you create the motional EMF, but you can also cause that EMF if you change the magnetic field. Remember when I was talking about the electric field not being zero and what I had said initially? I said, or you can have a change in magnetic field that's going to do the same thing. So Faraday realized if you change the magnetic field or if it moves, that's going to induce a current. And so he came up with an equation, Faraday's law. Well, it's not written here, so I'm going to write it here so I can go on. Faraday's law says the induced voltage remember, EMF is what we call it for a battery, an electromotive force, a force making charge move. Well, in this case, it actually was a force making charge move. It actually makes sense here that induced EMF is equal to minus, and I'm going to write this, there's two different ways of writing it. N delta V subscript B over delta T. And of course, at this point, you should all be looking at that and saying, well, great, that meant nothing to me. I mean, isn't that the case?
I'm trying to figure out what letter that is.
This here?
No, the
Yeah.
Oh, come on. Not a member of Phi Beta Kappa?
No.
That's Phi or Phi. Nobody calls it Pho or Pho. The F in Greek. So this here is what we call the magnetic flux. This here is not something surprising. The number of, number of loops. So this is saying if I have loops with magnetic flux, which I haven't defined yet, I realize, that is changing with time, then it's going to produce a voltage. So what is magnetic flux? Magnetic flux, I have lots of slides devoted to it coming up, but it is the amount of magnetic field going through a surface. So your loop is defining the area of the surface, and the flux is how much magnetic field is going through that surface. So we're going to have to look at how to calculate that in just a moment. So, and the minus sign. The minus sign has a very important purpose. Look at Lenz's law. I haven't talked about Lenz's law, but I will. And that's the purpose of that minus sign. Lenz's law is the law that tells you what direction the current is going to flow, or which side's going to be positive and which side's going to be negative. So Lenz's law is an important part of Faraday's law of induction. And that minus sign to me just says, look at Lenz's law. In practice, we do have some vector equations that this comes from, and it does come out of the math. They didn't just put it there to remind us of Lenz's law, but that's the way it should work for you. So here's an example of Faraday's law of induction. If you look at the upper picture, the magnetic field is weaker than the lower picture. How can you tell that the magnetic field is weaker in the upper picture than the lower picture?
The amount of X's.
The amount of X's. Remember, those are magnetic field lines that are going away from you. And so in the lower picture, there's more magnetic field lines inside the circle. Hence, the amount of magnetic field going through that area is bigger. That's bigger flux. So the flux is increasing with time. So if the flux is increasing, that means delta flux over delta time. is a positive value. And so if I look back at Faraday's law of induction, that delta flux over delta time is a positive value. I have the n, that's the number of loops, and my picture was just 1. Minus sign, the voltage would be negative, but it doesn't mean anything if I just have a loop that the voltage is negative. But this situation should produce a voltage. And how do we determine the direction? That's Lenz's law. So here's the rule for Lenz's law. Lenz's law says that the induced current will create a magnetic field that opposes the change. So in this case here, the magnetic field got stronger, right? And so to oppose that change, I need to make a magnetic field that's in the opposite direction. And so that means I need to make a magnetic field that's pointing out. Well, if the magnetic field is pointing out, what direction is the current in the loop to create that? You point your thumb in the direction of the magnetic field and wrap your fingers, and it says the current is going to have to be going this direction, which would be counterclockwise. And so that's what the minus sign is reminding me to do. Look at Lenz's law. So going from the top picture to the bottom picture would induce a counterclockwise current in that circuit, or in that loop. And then I would have to know some more information to get how big it is, right? I have to know exactly what the flux change is per time. Because this doesn't have time or actual magnetic field strength. What about if I went from this situation to this situation? What would happen then? Magnetic flux is now getting which way? Stronger or weaker? Weaker.
So you have to go into it.
Right, to try to keep it the same. And so then my fingers go like this, and it's a clockwise. So if we went from the lower one to the upper one, it would be a clockwise current. If we go from the upper one to the lower one, it's a counterclockwise current. That's Lenz's law. Now calculating the flux. One way of calculating the flux, theoretically, is to take the area of the circle times the number of, well, actually, we can just count the number of these. 1, 2, 3, 4, 5, 6 versus, 1. And then that's 9. So a total of 10 there, 11, 12, 13. So I went from 6 to 13 x's. So I'd say, my flux went up a little more than double. That's one way you can do it in thought. It's not very precise, right? So we want to be able to do that mathematically. That the upper one is telling us magnetic field is number of lines over area. I just going to get to the number of lines going through is proportional to the magnetic field that's perpendicular to the surface. It says perpendicular. What do we really say for three-dimensional situations? Perpendicular is to a line only. Otherwise, what should I say? Normal. So we're going to take the magnetic field that's normal to the surface. And in other words, we're doing normal to the surface. We define the direction of the surface as the normal direction. So the flux is equal to the magnetic field dotted to the area which has its direction normal to the surface. So that's how we actually calculate the flux. The magnetic field times the area times cosine of the angle between the normal to the surface and the magnetic field. So here's two pictures to help us get this straight. Now, people who are in Physics 252, we've already done this with electric field. It's all reviewish. People in 152, we didn't do this. You didn't say Gauss's law carefully. So in a picture like this, where you have the surface is normal, to the magnetic field, then we have B is pointing up and A is pointing up. So theta, the angle between the two, is 0 here. But in this case, I have my B is up, but my area is in the normal direction like this. And so there we have the angle between them is not 0. And there's going to be less flux. If the reason for this picture is for you to count lines. If you count the number of lines that go through the area in each case, when it's tipped up, these last two aren't going to be going through it for the same area. So you'd have less flux. Although when I look at this picture, it's hard for me to tell that these ones are not going through it. It looks like they are, right? So the picture is not the best at indicating that. So units. We have a special unit. I don't know what that rectangle is, but it's a leftover from something I did silly. We have special units for the magnetic flux. Its units should be Teslas for magnetic field strength and meters squared for area. And so we define a Weber as a Tesla times a meter squared. And of course, even though my last name is Webb, not Weber, I still like this unit because if I had come from a Germanic background, then my Webb would have come from the name Weber originally. But since it's a British background, it still means the same thing, by the way. My ancestors apparently made fishing nets. Good to know, right? So I say all of that just so you remember, oh yes, the unit of magnetic flux is the Weber. So here's Faraday's law in all of its glory. Notice I said there's two different ways of writing it. What's the difference in the two? The N. The upper one is saying, okay, if I have 3 loops, then the flux is 3 times, the area is 3 times the area of one loop. The lower one is separating out and saying the area is the area per loop and not even multiplied by the number of loops. I like the lower one better just because it's most explicit. So the flux linkage is apparently the name for N theta B. I don't care. What will not produce a magnetic field? So now notice it doesn't say an induced voltage, it says a magnetic field. We'll change the magnetic flux through a stationary coil. Induce a magnetic field.
Yes.
Yes is right. He answers like he's just boldly guessing, but you are right more than you're wrong. So I'm assuming there's some knowledge in the background. Yeah. You guys didn't grow up in my era or in my high school, but a little bit, not too much, was something we said all the time. So it's going to induce a magnetic field because if we induce a current in that coil, that induced current is going to induce a magnetic field. And so if you change the magnetic flux, according to Faraday's law of induction, change the magnetic strength, changes the flux. Actually, that just says flux. Change the flux, you're going to then induce a current, which then produces a magnetic field to oppose the change. Okay, moving a wire through a constant magnetic field. When you go from stop to moving, you could say yes, because when you go from stop to moving, there will be a rush of current. But once you're moving at a constant speed, you're at equilibrium in terms of, you just made the electric field that has the right strength to counter the magnetic force. There's no longer any current, hence not producing a magnetic field. The last one, moving a coil. Go ahead.
So as long as you're changing speed.
If you're changing speed, then you will, right. But if you're going at constant speed, you won't. So it depends on if it's constant or not. If you twirl it, what about that?
You're rotating it? I'm not sure. Yes.
Yes. And it's like 2 for 2. Okay, moving a coil through a constant magnetic field. Gonna go for 3?
I'm going to say.
So close.
I'm going to go with. Oh, I don't know.
No, you're right.
No?
No.
Hey!
No, because you have to have a changing flux. It's a constant magnetic field, and if you're moving at constant speed, you're not going to have a changing flux. And so you're not going to be changing anything. So you'd have to have a changing speed to have a changing flux. Now back to all those slides I skipped. There was a question here. Let's start with this one, then skip the question. If I go from A, B, C. So if I'm an A, I have a loop that's moving in a constant magnetic field at 0. Am I going to have current produced when it's in A? So it's just moving in a region with no magnetic field. Okay, Trey says no, and you're correct. Why is no the correct answer?
Because there's no magnetic field.
Yeah, there's no magnetic field. There's no magnetic flux. You have to have a changing flux, so no flux means nothing. It's staying constant at 0. You can momentarily have 0 if it's changing and still be working. But a constant flux, nothing. What about B, where it's going from no field to field?
There is a change.
There is a change in the magnetic flux, so that's going to induce a current. Now, the big question, the reason I have this, what direction will the current be?
Well, the force has to oppose it. So that means the current's going to go this way.
Okay, when he said the force, he meant the change, that the current has to create a magnetic field that opposes the change in magnetic field.
Yes.
Well, force wasn't the right word, but the thoughts in your head were the right thoughts. So the magnetic field is pointing this way, and since it's getting stronger, then we need an induced magnetic field that opposes that. And so we need our induced magnetic field to make a magnetic field that comes this direction. So we are going to have, now I come here and I'm going to write it wrong unless I look at this. So we're going to have a current that goes like that to make a magnetic field opposing the change. Okay, what about when we're in position C? Are we going to have a current there?
If we're just sitting there.
No, it's moving.
It's constant from C to what?
While we're in the region C, so while we're in the region of constant magnetic field.
Oh, then yeah.
No induced current because it's constant magnetic field. Constant magnetic flux is the important thing here. And what about finally D, going from the magnetic field into no magnetic field? My front table is totally down with this, just so everyone knows. There is a changing flux, hence there's going to be a current. And what direction is that current going to flow?
It's going to go the other way.
It's going to go the other way because
our flux is going down, and so you need to have a flux opposing the other direction.
opposing the change to try to keep it the same. So it's going to go this way this time. So coming around once again. So I have, the current going that direction in D. And of course, the last one would be the same as A, so there's nothing to consider. So notice it says for each one, specify clockwise, counterclockwise. So B was counterclockwise, D was clockwise, the others were 0. Okay, magnetic electric generators. Now what your group is doing. So magnetic generator, when you look at that, it looks exactly the same as the picture we had for electric motor. Exactly the same. Well, you do have to realize this said south and north, so that was a magnet. So we have a magnet and we have a coil that rotates inside the magnet. That was the electric motor. Remember I had the electric motor up here? We connected to a battery and it worked? Yeah. So an electric generator is just the opposite. Remember I used the comparison to heat engine versus heat pump. The heat engine, you put heat in at high temperature, you exhaust heat in or heat out at low temperature, and you are converting thermal energy into mechanical energy. The electric motor, you put electricity in and you convert that electric energy into mechanical energy. The heat pump, you put a mechanical energy and you pumped heat. The electric generator, you put a mechanical energy and you pump charge. So they're completely analogous. And so it's no surprise that the design is actually the same. So you have the magnets here. If I run current, wait, this is a generator. If I make this thing turn as indicated in the picture, then I'm going to have the wire moving, and we could use what we started with today and say, oh, there's going to be a force to create a voltage difference on this piece of wire, and there's going to be likewise a voltage difference on this piece of wire, and we could calculate what those voltage differences are. Or, much easier, we can use Faraday's law of induction. We can say, the induced EMF is equal to minus N delta theta subscript B. The reason for the subscript B is because it's the magnetic flux rather than the electric flux over delta T. So in this case, there's only one loop, but I'm going to go ahead and keep N there. And then I have to calculate my flux. Well, the flux was equal to B dot A, which is going to be B times A times cosine of the angle between them. Well, if this is rotating at a constant speed, then I could say, well, theta is equal to omega t, where omega is the angular frequency. And so my flux is equal to BA cosine of omega t. So my induced EMF, Michael, minus N, if I have a constant magnetic field between those two poles, which I certainly should, and I have a constant area on my loop, which I certainly should, then I can bring those outside of the delta. Whoops, I put delta flux BA. Delta parenthesis BA cosine omega t is what I should have put. At this point, we turn to our friends with calculus. Delta, in calculus, that becomes a D, right? Because delta means changing for a finite size. D means a change for an infinitesimal size. The true form of this all the way from the beginning was this is N d theta dt. That's the true form. So if you take the derivative of cosine omega t with respect to time, what do you get? I'm looking at 4 people who are in my Physics 252 class. What's the derivative of cosine omega t with respect to time? Okay, it's minus, you have to take the derivative of the inside, so minus omega sine omega t. So those of you who are not calculus based, which is most of you, you don't need to worry about that calculus step, but recognize that there is the peak voltage that's going to be produced, and then it's going to be sinusoidal, sine omega t. So the peak voltage for the generator depends on the number of loops you have. So those people that are making a generator, if they get more loops, they'll generate more electricity. The strength of the magnetic field, if they have a strong magnetic field, they'll create more electricity. The area of their loop, bigger area, bigger electricity. And omega, how quickly it's rotating. Now, in the case of making your generator, you have to take into account how much force do you have to make this thing turn. Because the bigger the area, the bigger the number of loops, the bigger the magnetic field, the bigger the force necessary, the torque necessary to make it turn. So it's not just you have infinite energy possible if you make it big enough. But that's the fundamentals for how a generator works. So let's take the old school automobile. At some point, they went ahead and they put a generator in the automobile. Right? Because if you just run on a battery, like the automobile, we talked about the internal combustion engine, and you have the spark part. You have to have something with electricity to make that spark. And so instead of just having a battery that's going to run dead, yes, he's killed the third battery. Instead of having a battery that's going to run dead, you want to put a generator in there to charge it back up and to just keep producing electricity. So you take a little bit of energy out of your engine to create more electricity. And so they had generators, and of course, how did they start the old school cars? Get out front and you have a hand crank. I am not old enough to have done that. Just throwing that out there. So somebody realized along the way, wait a minute, I have a generator here. The generator is connected to the engine already, right? Because it's running off the engine. If I just take that generator and I force electricity through it, it becomes a motor. And so instead of going out there and cranking, I can just have some wiring set up that I will, instead of charging the battery from the generator, I will turn over the engine using energy from the battery. And so they use the generators to start it. Genius, right? Today's cars don't have generators. How many people knew today's cars don't have a generator? They have something that does the job, but it's not called the generator. What's it called? Alternator. Now, my high school physics teacher, who was really high in my estimation all my life, he died this last year, sad to note. He came to observe me teaching my first year as a college teacher. And I was teaching this lesson. And a student asked me, what's the difference in an alternator and a generator? Now, I didn't know, so I turned to my high school teacher knowing that he's all-knowing, and he didn't know either, which made me feel a little better about my lack of knowledge. But I looked it up. The difference in an alternator and a generator is an alternator is a completely different design that's designed to be more efficient at generating electricity. So it's still generating electricity, but it's a more efficient design. The alternator is made by having a rotating magnetic field. So you have a rotating magnetic field. If anyone's taken apart an alternator, oh, God knows why, you'll see that it has magnets, and the magnets come out and they have things like this that are interleaved. So you have a coil that's making an electromagnet. I don't know if it probably has a strong magnet in there to begin with. And then those come out. So this is north, this is south, and they go like that. Well, then that whole thing is rotating. That whole thing is rotating. So the magnetic field is rotating. And then you have coils outside that are stationary. The reason this works a lot better is because now the magnetic field is going to change from north to south with just a tiny rotation of the alternator. So that means you're changing very rapidly the magnetic flux. If you change the magnetic flux more rapidly, just look back at that first equation at the top of the screen. Change the magnetic flux over change in time. If the change is rapid, what's that doing to the voltage? It's increasing it. So you can increase the voltage quite a bit by having magnetic fields change back and forth much more rapidly. So one rotation, you have like 20 changes from north to south to north to south. And then those little coils are stationary. They're not flying about at high speeds. They're not going to be as prone to being torn apart by inertia, right? Because if things are going around in a circle, inertia makes them want to go straight. But since they're stationary, you don't have that. So it's more robust, it's going to last longer, and it's more efficiently producing electricity. So the difference in an alternator and generator is a generator is this, where you have a fixed magnet and a rotating coil. An alternator, you have fixed coils and a rotating magnet. The alternator will not work as a motor, right? That design doesn't work as a motor. So you have to have two now. You have a starter motor and you have an alternator. But the starter motor is optimized to be a motor. The alternator optimized to generate electricity. Okay. I'm just going to go right past this. We've already done all of this stuff. So if you have an alternator or a generator, it's going to be putting out an alternating current, because it's going to be going positive voltage, negative voltage, positive voltage, negative voltage. You connect that to a resistance, and the current's going left, right, left, right. And if you're rotating at a constant rotational rate, you're going to have a nice sinusoidal pattern, just like what we did in our beginning. So this is what your current or voltage, in this case voltage because it's omega NBA. And once again, I remember that voltage max is omega NBA. It's the women's NBA. The torque was I can't play in the NBA, INBA. The voltage is the women's NBA. So there are things I can remember. And T, by the way, here is standing for the period, the time it takes for one cycle. Well, let's say I want to do something in my automobile, like charge the battery. What happens if I connect this output to my car's battery? I get no good thing out of this. Because half the time it's going to be a positive voltage, half the time a negative voltage. That's kind of problematic. I want it to be a constant voltage because a battery is a direct current device, DC. And so I need something to make this so it's not going to change forward, backward, forward, backward. What did we do to make a motor so it could run off of a battery? Remember we had brushes and we had two pads. And so as it rotated, the brush would change which side of the loop it was touching so that it was mechanically changing the direction of of the current so that it kept the current going the same way. That split commutator, that would work for a generator to have a split commutator. But of course, we're using alternators in our car, so that's not an option with the alternator. So what do we do after that? This is just asking the question. Here is what we call a rectified voltage. Rectified is made all right. It's all positive. And how do we do that? Well, a split commutator, if it was just the generator I showed you, would do that automatically, right? You just place the brushes the right place. Otherwise, we use this thing that's called a diode. The way this works is it will allow current to go this way, but not the other way. A diode is a one-way gate for current. And so if I use a diode, I can connect things up so that I have both sides going to being the positive. I'm not going to spend time showing a one, well, I will. I'll show a diode bridge. Here's how you make a diode bridge. Here's your output that's sinusoidal. Whoops. So close. I got to the last one before I made a mistake. All right. The way this works is, imagine if this side is positive and this side is negative. How can current flow?
It'll have to go.
Current can only flow in the direction of the arrow of the diode. And then through these lower ones, it can only go that way. And so this side here will be positive, this side here will be negative, and these two don't allow anything through. Now we reverse it. So get rid of those. And now I'm going to have the current, so this side's positive. Which direction can the current go from the positive? Only the direction of the arrow. So now this one's going to go this way. This one, the current's going to go this way. And so I'm still going to have the positive and negative the same place. And so my terminals for this, great. My terminals for this are I just connect the two outputs of my generator, one to here, that's the positive terminal, one to here, that's the negative. and I will constantly have the voltage in the right direction. But if you connect this to your car battery, it's still not that great because you go up to say you go up to 15 volts down to 0. Well, your car battery's running at 12. When you go below 12, it's trying to put current through this because it's higher voltage. So we have to go a step beyond that. And let's see, do I have a picture? Here's questions we already talked about. I don't have a picture. What you do, what can we use to store energy? A capacitor. So what we do is we put ourselves a big old capacitor here. And that big old capacitor will then level things out. So the output of this might be something like this. That would work for the car battery. Of course, we don't like to have wiggle. The bigger the capacitor, the less wiggle you're going to have. It also has to do with how much resistance you have connected, because as you learn with the transient circuit, you have that RC time constant. And so the bigger capacitor will make it more stable. It's just storing energy to give it back so you have a stable voltage. We often then will take what we call a voltage regulator. We can do that with a Zener diode or something like that, that will cut it off and just make it so it's constant without ripple somewhere below that ripple level. Okay, we're out of time. Have an excellent weekend.